I'm seeing the same thing on both screens. There we go. Okay, welcome back. Today I'd like for us to finish up section 1.4 in the text. It's taking a brief look at the use of your graphing calculator. If you have one and use one, it's not mandatory in here. And it also addresses the computer a little bit. We'll get plenty of that when we look at Maple work in here. So I'll kind of delay that till we get to the Maple. I think we ended with this problem right here. F of x equals sine of 50x. And most of the issues that your authors address in chapter 1, section 4 are issues of the size of the viewing window. So just be careful, because sometimes you look at a function kind of in a micro versus a macro view, and you get a different picture of what that set of points actually is. So these are all representations of the same function, f of x equals sine of 50x, depending on the range of values, actually the domain that you plug in as well as the range, although the range in this case is the same. And I think we quickly analyzed why that was the case. The sine of 50x, if you take the period, the normal period of the sine function, in fact I think this is more or less what we ended with. Let's try another one here. So we take the normal period of the sine function, which is 2 pi, and if we divide it by this coefficient 50, we get pi over 25, which is not a very large number. So this thing goes through a full sine cycle every, what did we decide that was? 0.125? What, is that right? So that's not a lot of space for it to begin to repeat itself. So that's why the viewing window can, as you vary the viewing window on your graphing calculator, you're going to get a completely different looking picture. Because this thing's going to repeat itself quite often. Let's go on. Same basic premise. If you look at a function y equals 1 over 1 minus x, these are the kind of things I think you ought to know when you enter these in to your calculator, or you look at this problem in your textbook. You ought to think to yourself, this function, this graph has some difficulty at x equals 1, right? At x equals 1, what would you describe as going on there? Asymptote. Okay, what kind of asymptote?
Horizontal.
Vertical. Okay. So as at 1, certainly this function has problems, major problems. And in fact, doesn't it have problems near 1? So when you enter this into your calculator, and you look at it from negative 9 to 9, you may see, in fact, the vertical line that is serving as the vertical asymptote. Now, that may vary from one graphing calculator to another, but that line will appear. Don't mistake that as part of the graph. It's not part of the graph. It's actually a boundary for the graph. If you close in on that and look at it maybe from roughly negative 5 to 5, that will no longer be there. And it'll just be the graph itself, which you can see on the left side of negative 1 goes to positive infinity, and on the right side goes to negative infinity. So not only does it have problems at 1, it has problems near 1. And we've seen that come into play then in terms of limits, and limits are important in calculus because a derivative is a limit, and we need to know how to take limits. Let me relate this to what we're going to be doing in calculus. We've already talked about slopes of tangent lines. And if we look at a function like this and we want to talk about the slope of the tangent line, we would want to take a picture like this. And as we want to get closer and closer to this bad value of 1, maybe we're right here. We want to talk about the slope of the tangent, or right here, the slope of the tangent, or right here, the slope of the tangent. What's happening to those tangent lines? They're getting more and more vertical, right? Mm-hmm. What's the slope of a vertical line? Or let me rephrase that. What happens to the slope as the line gets more and more vertical? What's happening to these slopes? This tangent to the curve, this tangent to the curve. What about these slopes? Aren't they getting more and more positive? The larger positive numbers, right? So as we come in from this side, the slopes are approaching positive infinity. Would that be a correct? Okay, so what happens as we come into this bad value of 1 from the other side? What kind of slope is that? Negative. Isn't that negative, in fact, even more negative? Mm-hmm. And that's even more negative, right? So do you see how it's got problems as it approaches 1? On one side, the slopes are getting very, very large. Positive means it's increasing very rapidly. And on the other side, we've got slopes that are negative, and in fact, getting more and more negative, so they are decreasing very rapidly. So these are the kind of things that we're going to analyze in calculus, and that's why being able to picture functions like this are important to us. So again, the viewing window has some importance. Here's a unique problem. This may or may not be the case on your graphing calculator. The one on the left, and notice it's the same domain and range, the one on the left, depending on how your calculator actually figures out values, you could plug in the cube root of x and it would give you the picture that's on the left. In fact, you may want to try yours if you have yours handy and plug in either x to the 1/3, or if you have some other way of plugging in the cube root of x. This is what the graph should be, right? Mm-hmm. Isn't it possible that if x were negative, can't we take the cube root of a negative number? Cube root of a negative is negative, right? So if x is negative, its cube root should be negative. There should be points down here. Now, depending on how your graphing calculator works, it may give you this picture. And the reason it may give you that picture is because it has done something probably in the figuring out of the cube root. It used logarithms. And because you put in a negative number, it's trying to take a logarithm of a negative number, and it's not going to work. So, I don't know, does anybody have a calculator that gives you this picture for the cube root of x? Okay, some of them will, depending on how they actually figure out the cube root. But this is how it should look. So don't always rely on your calculator as giving you the correct picture, because sometimes it varies depending on how it figured out the values for that picture. Okay, and here's another use of the graphing calculator, and that is to find the solution to equations. You maybe want to graph y equals cosine of x over an appropriate domain, and graph y equals x, and then superimpose them on the same axis system, and then you can gradually zoom in on their point of intersection. And some of your calculators, in fact, may have a feature where it will actually pick off the point of intersection. But as you look at this scale from -5 to 5, and then you get a clearer view of where the intersection point is, then you can zoom in on there and continue to zoom in until you can actually figure out to 2 or 3 decimal places what is an accurate x value, and if you can get to that x value, the corresponding y value where these two functions intersect. So that's another feature of most graphing calculators, that you can actually solve an equation by graphing the two pieces individually and then zooming in on the point of intersection. Do you use your calculator for those kind of things? Right? Graph them simultaneously and find the point of intersection. It's a handy use of your calculator. Okay? If there are any questions, let it be known now. I'm not going to assign any problems from 1.4. If you are new to using a graphing calculator, you may want to take a look at some of the problems in 1.4. It's my guess, tell me if I'm wrong, but it's my guess that most of you have been using graphing calculators for years, and you know, and you found every possible avenue that if you can use a calculator to solve it, you already know how to do it. That's my view on students in a Calc 1 course. Am I reading that properly? You know how to use them? You've been using them for a couple of years? And if you can at all use it to solve any problem, you use it, right? I don't blame you. Let's take a quick look into section 1.5 today. Again, review. Not trying to apologize for it. I'm trying to, as we go through these review sections, I'm trying to relate it to when we see it again, how we're going to see it, with either limits or slopes of tangents or any and all of that, because this is still pre-calculus material, but keep in mind calculus is right around the corner. 1.5 deals with exponential functions, so we're going to be looking at functions where the variable in the domain is in the exponent position. So we want to look at functions in that form. So let's analyze the different things here. Let's suppose that and these are some things I know that you've thought about most of these things, but we may touch on one thing today that for you is just kind of a different way of looking at this. If x is a positive integer, so let's say it's x cubed, or a cubed, x is 3. I know you know what that means. It tells us how many times we're going to use that thing as a factor, right? Mm-hmm. So it's used as a factor 3 times. So that works nicely for x to the 7th, x to the 11th, any positive integer. Let's suppose that x is 0. Now here's something I know that you know, but have you thought about why that's true? What is a to the 0? 1. Is 1, okay? Everybody knows that. Now, how many of you that just answered that are going to be able to explain that to me?
Well, because in the point of exponent that it's a times itself a certain number of times, so it's just a times itself no time, so it's still just a. Is that close?
Well, that'd be a.
All right.
Be that line of reasoning, right?
All right.
So I made it a separate category because I don't think it fits in here, because of what you just said. You were trying to use that number as a factor 3 times, 5 times. Well, how do you use a number as a factor 0 times? That's kind of hard. Anybody? Suppose I wrote this down. Suppose I wrote a to the 7th over a to the 7th. Would you know what to do with that? Do you know how to divide two things that have like bases? What do you do with their exponents? Subtract. Well, if they're the same, numerator and denominator, wouldn't you expect to get 0 when you subtract them? Right? So we get a to the 0. Now look back to the original problem. What is a to the 7th over itself? It's 1, right? Anything over itself is 1. So we can draw on a property of exponents that if you're dividing two things with like bases, you can subtract the exponents to come in and make some sense out of that, right? Now that's not going to work with 0 to the 0. Do you see the problem if we had 0 to the 0? We'd have 0 to the 7th divided by 0 to the 7th. I think we've got a problem there. So it's not defined for 0 to the 0. How about a negative exponent? So we're going to have the same function. So let's say that x is a negative integer. So could we do this? Could we say that a to the negative fourth is a to the 0 minus 4? Is that true? That's true. And wouldn't that be a to the 0 divided by a to the 4? Right? Kind of backtracking a little bit using that same mentality. And that to me looks like 1 over a to the 4th. Is that our definition of negative integer exponents? That is our definition, right? So we can kind of track that backward and see how and why that works. So now let's say that x is a rational number. So a to the 2/3. You know how to handle that, don't you? There's really two equivalent ways, distinct but equivalent to one another. What's the 3 tell us to do? Cube root. And then what's the 2 tell us to do? Square. So there's one way of looking at it. Take the cube root and then square the result. Do we have to do it in that order? Don't have to do it in that order. We could, in fact, square a and then take the cube root, right? As long as we, at some point in time, square and at some point in time, take the cube root. So suppose that I had something like a to the 1.8. That's a rational number, isn't it? So if I wanted to kind of say that it's completely and perfectly legal to raise a, or to raise 2 or 5 or 7 to the 1.8 power, what is a to the 1.8? I can tell you what it's not. It's not a used as a factor 1.8 times, right? Just don't complete the a, the second one, just like 8/10 of it. It's not that. I know that. I don't know much, but I do know that. So could we change 1.8 to a nice convenient fraction, rational number, right? How about 1.8? 1 and 8/10, 1 and 4/5. 9/5. Right? Do we know how to handle that now? Yeah, we just talked about that, right? Couldn't we take the 5th root of that? And then raise that to the 9. So all these things are completely possible. Positive integer, 0, negative integer, rational number. Now what gets a little tricky is an irrational number. Question?
We can simplify this further. Can we?
Can you simplify that? You mean as far as?
Like, we could take out 1a.
Yes. Yeah, if you had a number in here and we're actually trying to evaluate it, we could, I think we would probably want to look at it in this fashion, right? And there is a perfect power of 5 under the radical, so we can take the 5th root of a to the 5th. This is probably a good thing to bring up. Is that right? A to the 9th is a to the 5th times a to the 4th. So the 5th root of a product is the product of the 5th roots. So we're kind of stuck with this one because we don't know what a is and we don't have a perfect power of 5 and we're trying to take a 5th root. But the 5th root of a to the 5th is itself, right? So depending on the nature of the problem and what we're trying to answer, we may want to simplify part of that, but part of it we're stuck with. Part of it's not simplifiable. Well, let me change it from a to the x to, let's say, 2 to the x. Let's get a specific example. So could we take 2 to the third? No problem. We know what that means. Could we take 2 to the negative second? No problem. I think we know what that means. Could we take 2 to the 0? I think we've addressed that already. Could we take 2 to the 1.1? I think we could change that to a normal looking rational number, a fraction. Or 2 to the 1/4. So all those, we've already addressed all those. Now the question is, what about 2 to the pi? Pi is irrational. So it's not like we can take the cube root of it and then square the result. We don't have a definition like that. So we got to fill this in, because if not, we can't connect all those dots in this y equals 2 to the x curve. So would you say that 2 to the pi is somewhere between 2 to the third and 2 to the fourth? Right? So could we kind of, like we did on the graphing calculator just a bit ago to solve that equation, could we gradually close in on this window and sandwich this irrational 2 to the pi between two rationals, right? So we could come in and say, yeah, actually I think it's between 2 to the 3.1 and 2 to the 3.2. Is it in there? And then gradually we could get closer and closer to this 2 to the pi by closing in on it from either side. So we can get whatever level of accuracy we want to get by just kind of doing this procedure. 2 to the 3.14, 2 to the 3.14, let's say 1 here and 2 here, right? Right, isn't it 3.141592.6? It's been figured out to several 100,000 decimal places. That's an interesting question. In fact, it becomes a calculus question. How can you come up with a simple, relatively simple, calculus problem that you could put into a computer that would actually compute pi to 100 places or 500 places? Are we going to be able to answer that? We'll come close to answering that by the end of this class, because we can set up a pretty simple integration problem that the answer to the integration problem is in fact pi, exactly. Okay, so does that seem believable? We could kind of sandwich that between two rationals and always come up with the value of that irrational number? Yes?
Can we use the fraction form of pi, 22 by 7?
That's a good point. Is that equal to pi?
Not really.
Okay, so pi itself, now how do you know that pi is not equal to 22/7? Down deep in your soul, how do you know that? What kind of a number is pi? It's irrational, right? So if this is an irrational number, we're saying it's equal to a rational, right? So there's no way. There's no way pi, being irrational, could be written as the quotient of two integers, right? In the form of a over b, where a and b are integers and b is not 0. Does that sound familiar? Can't do it. Now, is that a pretty good approximation for pi? Pretty darn good approximation for pi. So it's okay to say that pi is approximately 22/7, but it clearly is not equal to 22/7. That's a different kind of number. That's a rational number. So we can take a function like 2 to the x, and we can have positive integers, negative integers, 0, rational numbers, and we can also fill in those little places where the irrationals are, and we can come up with a complete picture by plotting some points. 2 to the 0 is 1. 2 to the 1 is 2. What's 2 to the negative 1?
1/2.
Okay, 1/2. 2 to the negative 2, 1/4, and so on, right? So we're kind of asymptotic to the axis there. So there's a sketch. Now, I connected all the dots. And the reason I can connect all the dots is because we can put in anything we want to for x. The domain is all reals. So that allows us to basically take those dots and fill them all in that particular pattern. Now, we're going to be talking about slopes eventually in this class. Give me a feature about this function, 2 to the x, that we can then relate that to slopes. Try to envision a bunch of different slopes here. The slope at this point. The slope at this point. The slope at this point. What about all these slopes of all these tangent lines? Okay, the function is increasing, therefore the slopes are positive. So that's an idea we want to associate those two ideas. That's very important. If the curve is increasing, the slopes are positive, always. Slopes are positive at any point that we choose. All right, there's 2 to the x. So we know what this looks like. How about 1/2 to the x? So we've got this guy right here. We just sketched it. Roughly looks like that. How about 1/2 to the x? Well, I don't want to mess with 1/2 to the x. Isn't 1/2 the same as 2 to the negative first? Is that right?
Mm-hmm.
And then what's 2 to the negative first to the x?
2 to the negative x.
2 to the negative x. Now, does that help the cause? That helps me. I'd much rather graph 2 to the negative x. Excuse me, than 1/2 to the x. Can't you just take the x's and what were positive, they're now negative, and what was formerly negative is now positive, right? So if that's the case, if we're basically interchanging the roles of the positives and the negatives, we should be getting over here at -1. Now that's being negated. We've got to get 2 to the first. So shouldn't we get the mirror image on the other side of the y-axis? That 2 to the negative x? If I were to superimpose those, what point do they have in common?
0,
0, 1. In fact, isn't that a common point for all exponentials, regardless of the base? Right? 3 to the 0, 5 to the 0, 7 to the negative 0. So they all will go through this point. And then they have a variety of shapes based on the nature of the base of the function. Now, so if the base is greater than 0, if the base is greater than 1, will they all have this general shape? If the base is 5, the base is 7, the base is e. By the way, is that a comfortable number for me to use, e, in this class? Relatively comfortable with the number e? Can you give me a decimal approximation of that strange number? 2.718. Okay, we'll spend some time with that number either later in today's lesson or certainly tomorrow. But the number e is a very important number in mathematics and certainly a very important number in calculus. So we'll talk about that. But if the base is larger than 1, it's going to look like this. If the base is smaller than 1, obviously we're talking about a positive number though, won't it have this kind of shape? Right? And then we've got the ultra exciting example of when the base is 1. What's that look like? Not very exciting, right? because 1 to any power is itself. So that's just the line y equals 1. So I would probably leave that off of what we're taking a look at here today. Not a very, it may be exponential, but it's not, there's not very much to it. I think that would fall in the linear category. But we should expect graphs like this if it's increasing. Graphs like this have a decreasing flow to them. And what do we use them for? Well, we could model real-life phenomenon that are, in fact, something is growing. You can model a growth function. Something is declining in size or number, we could model a decay function with exponentials, and in fact, we do. And I'd like for us to look at some examples of those today. One growth model and one decay model. Okay, before we get to those, how would you go about graphing? What do I have written down? 4 minus 3 to the x. With some graphing techniques that we've already hopefully mastered. And then using this new piece, this 3 to the x. So without a graphing calculator, let's get a rough sketch of where this is. So we might start by graphing, or at least getting a mental image of that. So y equals 3 to the x. Isn't that roughly there in the plane, right? A little steeper than 2 to the x because the base is a little larger. Okay, if that's what that looks like, well, what we really have, I might rewrite this as negative 3 to the x plus 4. I want to kind of get the 4 off by itself so I know what that does. By the way, what does that do? Just takes everything and lifts it up 4 units. So we know what that's going to do. Let's get the other piece out of the way. How about negative 3 to the x? What's that do to this entire graph? Okay, it just flips it down, right, on the other side of the x-axis. So where the values were positive, they're now negative. Does that work all right? Right? Here it was positive 1. Now it's been negated. Now it's negative 1. So every one of those positive values has now been negated. Yes, sir?
If that had parentheses on a negative 3, would it switch around the y-axis?
You do have to pay special attention to where the parentheses are. Now, this is the negative of 3 to the x. And it's very different than from negative 3, the quantity negative 3 raised to the x. That's true.
Right.
So we do need to pay attention to the parentheses. This is this function right here negated.
Right.
Now that we have negative 3 to the x graphed, what do we do to that to finish this? Lift it up 4. So rather than trying to do this point by point, you might want to just go by the asymptote, right? What's the asymptote in this function? The x-axis itself. And now we want to make the line, what, y equals 4, our horizontal asymptote. So you want to come up with little tricks like that. So there's our horizontal asymptote. So we just kind of lift points up and throw them up here. So this point right here is 1 unit below the asymptote. Let's do that. Now, would I call that a graph? By no means would I call this a graph, but it's okay, right, for a sketch. That's a sketch. I don't know if it's a rough sketch or whatever, but that's an idea of where these points are in the plane by graphing techniques that we've already used, and then this brief review on exponential functions. Questions on that? Anybody? Okay. Another thing that combines some techniques that we've already used with exponential functions. How is that related to this thing that we've already sketched a couple times, 2 to the x? The fact that we're subtracting 3 from every x before we raise 2 to that power. Any takers on that one?
Just gonna move right 3.
Okay, and that what we've done to this point, right? The fact that you're subtracting 3 from every x before you put it into the function ought to take this thing and move it to the right 3 units. So if this is what 2 to the x looks like, then basically we're going to pick every one of those points up, slide them over to the right 3 units, and plop them right back down. So this is the point 0, 1. So there's our old friend, picked up, slid over to the right 3 units, and plopped right back down. So all those graphing techniques that we've already covered and reviewed in this course, we can apply now to exponential functions, hopefully. Yes, sir?
So will the graph still pass from 0, 1?
It will not, okay? And in fact, in order for us to get a y value of 1, what's the corresponding x value now?
3.
It's got to be 3, right? So there's that shifting. So by subtracting 3 from every x value, we cause things to happen a little bit later in the graph. Now, later in the graph means what? Further to the right. So that's why it's subtraction of 3 has the net effect of shifting to the right 3 units. So we don't get 2 to the 0 till we put 3 in for x. So we don't get 1 until we put in 3 for x. Okay, we know this is a function that increases fairly rapidly. We know this is a function that increases, y equals x squared, and eventually it begins to increase fairly rapidly. So as we move out to the right, so x gets larger and larger and larger. Which one wins? The exponential or the power function? Could you use your graphing calculator to tell you? Graph them both, right? After a certain point in time, one begins to dominate over the other, and they begin to separate so rapidly it doesn't have a chance of being overtaken by the other. Exponential, in the long run, will begin to dominate. Okay, this would be the dominant function in the long run. So squaring something, yeah, that gets pretty large, but 2 to some large power, 2 to the 15th, that's a tremendously large number. Much larger than 15 squared, right? So you should expect exponential functions in the long run to dominate over power functions. Okay, let's take a look at if we can look at 2 more problems. I think we've got time to do that today. Let's look at a growth problem. If I can find my picture here, we'll look at that. There's some data in your textbook that talks about a population problem. So I put some of that data together here on the same chart. This is the population, world population, over some 10-year periods. So we've got the year in here on the t-axis or the x-axis, and the population then on the p-axis or the y-axis. And these points are plotted. And actually something that progresses in this fashion, although it may not be exactly exponential, that's pretty close to an exponential function. I think we could find a function that would model this population growth pretty closely. And in fact, the authors have done that. Now, you're not responsible for this at this point in time. The authors have, through some regression formulas, have found a formula that doesn't fit this curve exactly, but it does a pretty good job of fitting this data. Now you say, well, let's examine where it is kind of not doing a very good job. Well, if you examine 1930, you can think about, even though the U.S. population, isn't the world population, but we had something going on in the 30s that may have affected the world, right? We had a depression, which may have affected world population. What's going on in the 40s and 50s? What's going on in here? Why is this bad?
The wars.
World wars, right?
Didn't have any guys in the country.
Right. So, not only did that affect our population here, but, the world was at war, or a great deal of the world was at war. So you can see how those kinds of things thrown in here, they affect what might have been by nature a nice exponential function, but it gets changed slightly. But this curve right here does a pretty good job of modeling world population from the year 1900 to the year 2000. Does a pretty nice job. And it is clearly that exponential. Now, when we say exponential, that means the slopes get larger as you move further out to the right. So if the slopes remained the same, what would that be? What type of picture would it be where the slope is the same all the time?
Linear.
Linear, right? But if the slopes are increasing as you go, then that is a prime candidate for an exponential function. Now we're gonna model one ourselves here in just a minute. Again, how this was arrived at, you're not responsible for that at this point in time. I'm sure you've used mathematical models. Tell me if this seems like something you've done. Does that look familiar? Have you used that, something like that before? That's got that stubborn little number E in there, which we're going to talk about tomorrow. How about this?
Yep.
That ring a bell? Those are the same. That first thing that I wrote down and the second thing that I wrote down are exactly the same mathematical model. What is this? This is what, the final amount of money, or the amount of money later, at some point later. This is the initial amount of money, right? The principal. This is the number E. This is the interest rate, growth rate. This is time. That's all this is. This is the initial amount of whatever we're talking about, Y. This is the growth rate. This is the time. So these are exactly the same mathematical model. So if you've used one, you've in essence used the other. And we're going to talk about those after we introduce the number E. Okay, let's look at a decay. Let's say that, and I'm just going to make one up, let's say that we have a radioactive substance. And let's say that its half-life is, let's say it's a fairly benign substance. Let's say its half-life is, 12 days. Somebody want to explain to me and the rest of the class and all those thousands of viewers watching us on cable TV, what is half-life? What's that mean?
It gets half after every 12 days.
Okay, the amount decomposes into half of what it was, right? In this case, every 12 days.
Yep.
Is that a foreign concept or a pretty, you've examined that before? Okay? So let's suppose we want to kind of build our own function here. And we want to come up with a function that we can put in some x value into this function and do what it says to do with that and come up with then the amount of stuff that we have left. So we actually want a function of time. And in fact, we want to allow for the fact that there might be a number there, a coefficient. So we want to possibly come up with a function, some number b times a, whatever a makes sense in this problem, to the t power. Well, I don't know what I want to occupy that b position, but I do know what I want for a, because this is a half-life problem. I want a half to occupy that position. Now, if I put a t there, will that work? So I want to be able to plug in a certain amount of days into that t position. And then when I plug that in, I want it to generate how much of that radioactive substance is left. Let's say that we have 24 grams of this radioactive substance. Okay? So I want to plug in 12. And keep that in mind. When I plug in 12, I want that 24-gram original substance amount to be half of that, right? Let me plug in 24. That's our initial amount here. Now, if t is 0, does this work? At time 0, do we have 24 grams? That works. But if I plug in 12, this doesn't work, right? Now, what can I do to kind of doctor this up just a bit so that when I plug in 12, I have half of 24? How about if I did this? T divided by 12. Now, does that still work with 0? When I plug in 0, do I still get 24 grams? I still get it. When I plug in 12, do I now get half of 24? Okay? When I plug in 24 for t, does it still work? Should I have a fourth of my original amount? Is that right? Because after 12 days, what happened to 24 grams? Didn't it get reduced to 12, right? Now let's start there with 12. What happens in 12 more days? That 12 gets knocked down to 6, right? Is that 1/4 of the original amount? It is. So I think this would be a function that would work for this situation, right? Now we could keep the base at 1/2. That, to me, when you look at it, looks more like a decay problem. We would expect that with the base less than 1. Or you'll see this done. 1/2, I did this before, is really 2 to the negative first. So 2 to the negative first to the t over 12. And that's another way that you can tell something is a decay function because of the negative exponent. So you can see it because of the base itself being smaller than 1, or because the base is larger than 1, but the exponent is negative. So that could model a decay function as well as a growth function. Okay, next class we will take a look at in depth at this number e. If you want to get a start with these problems, let me give you the problems at the end of 1.5 that I'd like for you to be working on. not responsible for them yet until we actually finish. This is page 63. Okay, I think I'll stop with those, and I'll give you some more when we're finished with this section.
Maybe handing
We will not be handing these in.